All right, welcome back to IS50B. We're going to be talking about binary space partitions today. We're going to be talking about the Painter's algorithm, which is an old school way that isn't used anymore, but might be interesting to some of you. And we're going to talk about Z buffering, which is how, if you've got two triangles that draw to the same part of the screen, which one appears on top. So, back in the day, if you had a screen, like this is your monitor, one way that you could handle two triangles kind of covering the same area, right? Like imagine you have one triangle there, one triangle here. One way you can handle it is by just doing wireframe, right? If you have a wireframe thing, you don't have to fill it. You don't have to figure out which one comes on top, all right? So that's one approach you can take, just drawing wireframe. Drawing the edges of triangles is, of course, faster than drawing the whole triangle and having to fill it, all right? When you guys all did filling, you go through and you kind of fill all the pixels in here. So back in the day, they thought it would be too expensive to do Z buffering, which we'll talk about later. It was considered outrageously expensive. It was the cash money approach that nobody could afford. So what they realized was there's a couple different approaches they could take. You guys didn't fill the triangles? Okay, well, maybe that'll be your next 7. Can you do barycentric? Okay. Is Megan the only person that did barycentric? Yeah. Okay. Then maybe we'll do Z buffering and filling at the same time. So suppose this one is in the back, and then this one is in the front here. What you could do is you could just fill this triangle first, like that. Let me give it a solid color. Maybe. Nah, it'll be rainbow. And then this triangle in the front, we can make this one a red triangle, and then we can fill it and just basically overdraw all of the pixels from the back one. And so this is called the Painter's algorithm. Because it works like you're painting a wall, right? You put down your base coat first, and then you put another coat of paint on top of it, then another coat of paint on top of it. Whichever coat of paint you draw last is the one that appears. And so this works pretty well as long as you can figure out which triangles are behind which other triangles. Like if you're in a room, you know, and you're here, and maybe there's a box in front of you, right? There's a few different triangles you're going to draw. Let's say your field of view is like this. We can reject all of these triangles back here. Why? Because they're outside of the frustum. We can clip this triangle here so that all this area over on the left-hand side here is discarded because it's outside of the view frustum. You can clip it to just this zone here. We can draw this triangle. There's going to be a triangle here. You can draw that one. Draw it in white. Terribly in white. I'll draw it in white here. So we can draw the white triangle there. Well, it's technically a quad, so it'll be 2 triangles, but whatever. This part of the triangle will get drawn, the galaxy color one here. The one on the south side here, this guy's also going to get clipped. So that triangle, so like let's say the triangle is kind of like extending off the edge of the screen, you know, like the edge of your screen's like here. What it does is it cuts it, right? It clips it. This is called clipping. Just cuts the edge off. Don't have to worry about it no more. So we've got at least 3 triangles on the screen. Technically, these are going to be quads. They're going to be 2 each, but we'll just pretend they're 1. Then we've got one other triangle that we probably need to draw. And I'll do that one in purple. And that one's here. Okay. Assuming the camera is like coming out of here somewhere. Okay, so why did I not need to draw these 3 sides of the box? Why can I just kind of come in here and just erase them? Why do they not matter for my rendering? What do you guys think? I'm running out of colors here. Blue. Okay. So Bruce, can I see this side of the box? Is it visible from where my player is over here? No, it's not. No matter how you pick up, like, I got some floss here, right? So you can see the Oral-B logo on the front here. If I rotate it around, you can't see it anymore, right? it's transparent, so maybe you can. I don't know. Transparency throws all this off. But the back side of a box you can never see. You can never see the back side of a platonic solid. Platonic solids are solids we're friends with. So X-ray powers, or you just have a translucent, transparent thing like my floss here. So these sides here can't be seen. And one of the ways we know that we can't see them is by doing something called back-face culling. And so depending on the orientation 1, 2, and 3, if the points go clockwise, you don't draw them, I think. By default, it's a convention. I believe clockwise you don't draw them, but if you were to flip it around, if I were to mirror this, 3, 2, 1, then the points go clockwise, counterclockwise, then you would draw it. And so in such a way, as long as you make sure that all of your triangles are counterclockwise while they face you, if you ever have 1, 2, 3, and you flip them around, then they're now being drawn in the opposite order, and you just discard them. So backface culling will throw away 50% of all triangles in the world. So, do you guys understand that? So for any object in the world, and in OpenGL you can set which direction is cold and which direction is not cold, but I believe it's counterclockwise drawn by default. So if you have the backside removed, now in a situation like this, you can actually see the backside of the skull here. So you probably don't want to remove it. But for any platonic solid, like my monster here, you can't ever see the backside of any of the triangles, no matter how I rotate it. For any 3D solid, you can always just delete the triangles facing away from you, and you will never encounter problems. No matter how you're standing around a cube, this is the normal vector, right? You only have to draw the ones whose normal vectors face you. The ones where the normal vector is facing away, you don't have to, because you can't see them, because this is solid, right? The front-facing ones are going to block the view of the back-facing ones. You guys understand? Boss, or are you just going to troll my students here? So, he's just control it. Okay, fair enough. So here we can delete from existence, for at least the purposes of rendering, all of those squares, all the parts of the square of the box that are not visible. Trying to watch Kearney while getting distracted by this hate. Oh my goodness. Okay, so now we've got all of the triangles. We've removed all the back-facing ones. We've clipped away everything outside of the view frustum. Everybody behind us is gone, and we can do this all using linear algebra. It's pretty easy, pretty simple tests. But now we've got this problem. We've got a problem where we've got a surface of the box here, and we've got a wall here, and we need to know which one to draw first. So which one, Sean, should we draw first? Should we draw the white wall first, and then draw the purple over it, or should we draw the purple first and draw the white one over it? The purple one first. Interesting. So we're going to first draw the purple triangle, like this, and it's actually a quad, so looking at it from the view of this guy, we're going to see a box in front of us, and then behind it is the white wall, and so the white wall is going to be drawn over it and cover up the purple. Okay. So yeah, so we have to do the white one first. We have to fill the whole area of the white wall first, and then we have to draw the purple box over it. Okay? And then everything kind of, and people said, that your kindergarten coloring skills would never come in useful. When are you ever going to color in the real world? Well, there you go. Okay, so there you go. Yeah. All right, and then that's what you end up looking at, right? So you see the box, the purple box in front of you, the white box behind it. Now, how can we do this algorithmically? How can we make sure that no matter where our camera is, like if our camera's here, looking this way, which I guess I'm going to have to put the box back. If my camera is there, if my camera is over here, no matter which way I have the camera looking, I will always be able to draw the triangles in the right order. Back to front rendering, indeed. And that is called the painter's algorithm. The painter's algorithm involves sorting all of the triangles, and you draw the backmost one first, and then you progressively draw other triangles in front of it over and over again. Are you going to waste time and effort? Yes, you are. All this area here is going to be overdrawn, right? You're going to waste. Every video card has a fill limit on how many pixels it could fill. Invented by a guy named Phil, maybe. I don't know. And isn't that bad? Sure, it's bad. But here's the question: if you've got, a whole level, how are you going to figure out which one is furthest away and draw that one first, and then next furthest away and next furthest away? You could do an order n squared. For every triangle in the world, find the one furthest away, draw it. Then do that again n times. So if only are there algorithms that fix the triangles so they don't overlap? Yeah, when triangles overlap, you can't really use the painter's algorithm. If you have a triangle going like this, right, where they're like penetrating each other, there is no way of drawing them so that it will look right. You have to use Z buffering, the money option over here, which we'll get to. You can't use the painter's algorithm. The painter's algorithm only works when you've got triangles that don't overlap or interpenetrate each other. Flip it, and if there's something already there, not fill it. So there's a couple different ways that people have handled this. So one way that is called ray tracing. And unbeknownst to most people, you can actually do ray tracing in old school, like Doom style games. In fact, that's how they kind of did it. They would draw a ray going out on every column of the screen and see which wall they hit, like that. And depending on how far away the wall is, walls that are really far away are drawn small, and as you get closer to the wall, they're drawn bigger. And you do one of those for every column. Because Doom levels and Wolfenstein levels aren't actually 3D, they are pretend 3D. They're 2.5D is what they're called, technically. You can do this. You can just simply cast a ray on every column of the screen, and then based on how far away the wall is, you draw the wall either closer or further away based on the distance, and that's it. It's actually a pretty easy algorithm, which we'll probably get to in this class, because we got a lot of smart people in it. Okay. But for the painter's algorithm, we're trying to do it a different way, where we're drawing one triangle at a time. It's not a good algorithm, by the way. No. You guys are all smart. They're all, for those of you watching at home, they're all saying, "I'm not smart. Don't give me hard assignments." No. I'm aware of your capabilities. So you guys get the spicy version of 50B. So BSPs. All right, so let's do this. So let's say that you've got a warehouse. You got some boxes. We're doing this in 3D, right? You got some boxes. You got some storage units. Players over here or something. He's like looking at this. He's like, what can I see? Which one of these surfaces should I draw first? Let's put in one more. Doesn't have to be axis aligned. Okay. So you got object A, got object B, object C, object D. The surfaces that we could see would be this one, this one, this one, this one, and this one. Okay? All the other ones are invisible because they're facing away. Remember, the normal vector can tell us if we can see them or not. All right? Only the normal vectors that are pointing at us, basically you take a normal vector, you take a displacement vector to the player, you dot product them, and if the answer is greater than 0, then we can see that triangle. It's an easy way of doing it. So, or if you are doing the clockwise, counterclockwise approach, then that's a cross product of the two basis vectors of the triangle. Either way, easy. So, we've got this thing here, and let's say that, I'm not going to draw it, but we've got 1,000 boxes in this warehouse, and we need to know which one is the furthest away and which one is closest. And so we're going to draw D first, then we're going to draw C, then we're going to draw B, then we're going to draw A. We're all talking about peppers now online. Okay. So, all right. So how do we do this? How do we figure out which one's furthest away? Well, we are going to construct something called a binary space partition. And a binary space partition is a tree. It's a binary tree. Okay. A normal binary tree that we're used to in CSI 41 is used for like sorting numbers or names or things like that. So if you have the number 42, everybody to the left of it is smaller, everybody to the right of it is bigger. 30 to the right of it, 41 and a half, I don't know. That's your normal binary tree. A binary space partition is a binary tree, but instead of sorting numbers, it's sorting space. Okay? So what you do is you take a line and you draw it through the world somewhere. Like I will draw a line here. How you do this, how you pick this is actually a difficult question. But I'm going to call this line here, I'm going to call this one 1, or I, for sure. I'm going to get the player out of the way. We know where the player is. And I'm going to draw this over here. So that is the root split. Okay? So everybody in the world, every object in the world is either to the left, to the right, or straddling it. Right? Because I could have drawn this like through the middle of an object, right? In which case we could clip it, put half on one side, half on the other. So, who is to the left? Who is to the right? How many objects are there to the left of splitting plane 1? A is to the left, B, C, and D are to the right. Yeah. And so what we can say is if you have just one object to the left, we're done. And so I'm just going to put the letter A in there to indicate that this is something called a leaf node. Maybe I'll draw it in green to indicate there are no further splits in that direction. So A is to the left, and B, C, and D are to the right. And so since I've got more than one object here, I can split it again. And I don't have to do an axis-aligned split. Like I don't have to follow the X and the Y coordinates. I can actually split it like this if I wanted. There's something called a KD tree that follows the axes. We're doing a BSP, which can have any angle on it. And so this is split number 2 over here. So split number 2 is here. Who is to the right of split number 2 and who is to the left of split number 2? How do we decide how to split? That is the subject of many PhD theses. One heuristic that works reasonably well is you find the longest edge and use that as a splitting plane. So it works all right. What you don't want to have is you don't want to fracture these things into like 1,000 pieces, right? Because then it becomes degenerate. You also can allow, like, if you've got a lot of pieces that are like really like close to each other, it can be hard to find planes that split them apart. So what you can do is you just say like, okay, that's a leaf. And then if you ever come in there, you just check all 3 objects or something like that. So there's a lot of heuristics that are used in getting a good BSP. C is to the left. And that's a root node, or not a root node, that's a leaf node because it's only got one object in it. So we are done with that side over there. So C, and I'm going to, again, circle it in green because it's a leaf. And in computer science, leaves are on the bottom, of course. That's what a tree is. And then on the right, we've got 2 more guys over here. Or, sorry, on the left, because we're looking at it from that perspective. We need to do one more splitting plane. So I'm going to split it here. And then who do we have to the left? Who do we have to the right? Is C to the right? C is to the right of 2. You are absolutely right. Yes, thank you. Let's see if I can fix this. There we go. Nice. All right. So yeah, you're absolutely right. C is to the right of 2, and B and D are to the left. Okay. And then from this is splitting plane 3 here. So the ink back to white on that. This is splitting plane number 3. To the left of it is B, to the right of it is D. And there is our finished binary space partition. Yep. So these are they're dividing planes. They're an infinite plane, but the child ones originate from the splitting plane they come from. So they actually have a, yeah, you can think of them, sure, as a vector. So it starts from there and goes out this way. It doesn't split the world over here. Okay. If I had another object over here called E, I could like split it, and that's a separate split from the one on the other side. So they split the world into halves, and then each of those worlds can be split into half, and then each of those worlds are split into half, and they don't affect the other subworlds. Okay, it's a recursive data structure where you take a world and you cut it in half. You put half the things in one side, you put half the things in the other side. Okay, so now magnitude is infinite unless it collides with another plane. Yeah, that is correct. So they stretch on towards infinity and beyond. So this goes in both directions, I guess. So you're creating semi planes, or I think that's what they're called. So you're basically cutting the world in half repeatedly until you end up with, in this case, I have one object per leaf. In reality, you might have that be a threshold, so that you might allow like a couple different objects per leaf. Because otherwise, you might end up with just tons of splitting planes trying to get them all cut up. Okay, so now how do we tell who's in front and who is in the back? All right, here's our location. Let's say here's the camera of the person. Are we to the left or to the right of this plane? The player. Are we to the left or are we to the right? The initial plane goes in both directions. That's why I erased the bottom one here. It's going up. Okay. So we'll pretend that arrow down there isn't it? We're to the left of it, right? And so should we draw A first? Because A is, we go left here. We're to the left. Should we draw A first, or should we draw everything else first? If we're doing the Panner's algorithm, or we're drawing back to front, we draw everything else first, right? So we traverse the tree, and we can figure this out. Like if this is the origin, I got to erase around. Let's say this is the origin of the splitting plane down here. Displacement vector, here's the player's location P, and this is the location of 1. So P minus 1 is a displacement vector pointing this way. And then we have the left normal vector. And so we dot product them. So we dot product that with, this is the left dot producted with the number 1 left. I don't know. Terminology is terrible. I don't know. So we dot product these two things together, and if we get greater than 0, then we're to the left of the splitting plane. If we get less than 0, we're to the right. Because they're pointing in the same direction or they're pointing opposite directions. So basically, we now know that we have to draw everybody. So I'm going to draw using the galaxy pen. We're going to have to iterate down this way and draw everybody in that side first. And then we'll come back and draw A last, because he's going to be drawn on top of everybody else. Okay? And now we're going to repeat. So now we iterate down the tree. We're now here. We're at node splitting plane 2. Are we to the right or are we to the left of 2? So this is 2. Here's the origin. This is to the right. This is to the left. Are we right or left of 2? I'll extend it out if you want. For the math to work. Here's the displacement vector. We're to the right of it, okay? So do we draw C first? C's closer to us. Because do you guys see how we know this now? Because C is to the right, we know that C is closer to us than B and D. So who do we draw first? Do we draw B and D first, or do we draw C first? It is impossible for anything over here to be closer than this guy, right? They can't, or more specifically, nobody over here can overlap this guy. There's no ray that can be drawn in which B would be in front of C. Right? be more tactful about it. Yeah, so we're going to draw B and D first. Okay, rinse and repeat. So we're going to iterate down the tree structure to splitting plane 3. So for splitting plane 3, the origin is here. Extend it out that way. Are we to the left of it, or are we to the right of it? Left. So which one do we draw first? We draw the one to the right first, right? Because all of these things are telling us which one's closer to us. A is closer. Okay, great. We'll come back to you later. Let's do the other ones first. Which one's closer, B and D or C? C is. Okay, great. We'll do B and D first. Okay, which one's closer, B and D? B. Okay, we'll do D first, and then we'll come back later. And so the order that we draw the things is going to be D, followed by B, followed by C, followed by A. And if you do that, then you will paint all of these pixels first, then you will paint all of these, and these will draw on top of D, right? And then we will paint C on top of D, and then probably some of those pixels are going to overlap D. And then after we finish all that, then we draw A, and A is going to overlap B, C, and D. And so, yes, you're going to get overdraw, but it will successfully solve the painter's algorithm so that the ones furthest away get drawn first, then the nearer ones, then the nearer ones, then the nearest. Okay? That makes sense? So every time you're doing this, if you're drawing back to front, you can just simply do a dot product and be like, okay, let's draw the further away people first. Draw the further away people first, then draw the closer people. That's the algorithm. If you ever need to explain how recursion works, this. Yeah. You guys got it? And it's just, figuring out the splitting planes is the hard part on it. Like it is. I'm not going to downplay that part. But if you're handed a BSP, and you're told like, okay, here's a BSP that's got leaf nodes here and here, and these are the splitting planes. Yeah, all you have to do is just constantly say, okay, draw the further away half first, then draw the nearer half. That's your algorithm. If that further away half is not a leaf, you say draw the further away half first, then the nearer half. And you just keep recursing until you get down to leaves. You draw D, you draw B, you draw C, you draw A. Done and done. Okay? So is Voronoi kind of related to BSPs because they almost look similar? The shape is a coincidence. The shape is a coincidence. I am kind of drawing them like skin cells, I guess. But like if you had like a box here, I could feasibly split it like that, or you know what I mean? Like it doesn't, like there's nobody can tell me no, Like if I wanted to create splitting plane 4 up here, I could split it this way, and now E is on both sides, and then I'll need another splitting plane to split this E2 and E1, or like you can do it badly, really easily. Ideally, you want a splitting plane that will cleanly, cut as much as possible, because it's kind of annoying to have an object on 2 halves of the BSP. So yeah, EU is right. You can do it very badly. Like cut here, we'll cut here, cut here, cut here. Like you can do it really badly if you want. Okay, so another thing you can do with the BSP is you can actually use it to represent. You can use it to represent a map in Quake. Like this is actually how maps and Quakes are held. So rather than just holding objects within the world, you can actually have the BSP itself hold what areas are solid and what areas are not solid. Okay. And so, for example, instead of having like objects within, which you can have, like if it's an open area, then you can have objects inside of it. You can have different, monsters inside of a leaf and things like that. That's all fine. You can also do something like this, where you have a splitting plane, and you just say, okay, this whole area is water. Okay. Everything to the right of C over here, we need a new splitting plane. Is C to the right, or is it to the left of splitting plane 4? What do you guys think? C is to the right, and it is still an open leaf node, one that's like open space. Maybe C is a box or a pickup item or something like that inside of it. But to the left, you have a solid node. This is solid space now that is just water. Okay, just solid water over there. And so you can use a binary space partition to indicate which parts of your map are solid wall, which parts of your map are lava, which parts of your map are slime, are water, lava, slime, water, air, or solid. I think covers all of it. Might be forgetting one. Anyhow. And so now let's say that somebody let's say somebody throws an incendiary grenade. Okay? Air, earth, fire, and water. Yeah. So let's say that somebody throws a grenade. And it ends up somewhere within, your map here. Incendiary grenades do not go off underwater. Okay, so you have to do what's called a point contents test. And so we want to see if this spot right here is underwater. That's not really visible, is it? It's an incendiary grenade. We're using red. Okay, so the incendiary grenade wants to explode right here where I'm drawing these red spirals. Okay, and there's a point right there where it's its origin. And you want to say, am I underwater? Yes or no? Tell me. Here's how it works. So BSP to the rescue. Okay, so you start off at the root, right? You start off here. This is the root, right? First splitting plane. Are we to the right? Is this point over here? Is this point right here? Is it to the right or is it to the left of splitting plane 1? Right. Cool. So we recurse. Are we at a leaf? Nope. Okay, recurse down to the right. 2, splitting plane 2, right here. Covered up the 2. Let's make the water. I can draw this a little better. So splitting plane 2, are we to the right? Are we to the left of splitting plane 2? These are like waves now. And then our grenade is right here. We are to the right of splitting plane 2, so we recurse down to the right because we're not at a leaf. Now we're looking at splitting plane 4. Are we to the right? This is the right. Are we to the left of splitting plane 4? Left. And so we recurse down to here. Are we at a leaf? Yes, we are. Okay. If this was an open leaf, then you would have to do something like, say, am I touching a box or something like that, right? As, am I in lava? Am I open? Am I touching a box? Okay. But here, there's no objects in here. It's just this entire area is just solid water. I've marked off a, infinite demiplane of water, essentially, like in DD. And so this will return, you're in water. You are underwater. And then the grenade will go floop and make some bubbles, and nothing more will happen. And so by using a BSP, you can grab, am I in air? Am I in ground? You guys understand? At any point along the way. So you can use it to draw the objects in the world. You can use it to find out what's around you. Like if the player is here, you just be like, hey, tell me everybody else within my leaf over here. Because these are the only things I can interact with, right? So if I'm like trying to use something, the only thing nearby is like this, right? Yeah. So what's the nearest object to me? You can find that out too. So by using the BSP and traversing it, you can find out, where, what leaf you're in, and then look at the objects around you and stuff like that. Pretty cool stuff. This is the basis of Doom and Doom 2. They used the Painter's algorithm, kind of. They kind of did raycasting also. And then in Quake, they used solid BSPs to actually represent the entire world. So if you look at the blocky nature of like a Quake level, because they're essentially cutting the world Quake. Okay, it's not the Quake I was thinking of. All right, there we go. So this whole castle here is made by subdividing the world into halves. Okay, and it doesn't look terrible. Like it's not like a super high, like You know, you can count the triangles on it, right? But it's not ugly. It's fine. And so you just constantly chop the world in half and chop the world in half and chop the world in half using these splitting planes. And then the areas that are solid are marked as solid leaves. They can have a texture applied to them. Areas that are skybox, so that'd be another one, right? So the sky, like the sky box, is drawn infinitely far away. Essentially, you can see the distortion up here on it. So the skybox would be another place, like point contents test. You're out of bounds. You're in the sky. Delete myself. Okay. It's interesting we've come full circle and people intentionally make blocky games. Yeah, there's a certain aesthetic to it that is honestly appealing to a lot of people. You don't need to have maximum graphical quality in every game, especially because it takes a lot of art budget to make really high quality detailed art. And so a lot of games are like going for the retro style simply because it's cheaper. It's much cheaper to do so. Yeah, you can see how these blocks, and you guys get that, like you just plane, cut the plane, cut the plane, cut the plane, and just mark these areas as solid. All this area over on the right is just marked as open. You got some objects over here, so if you want to see if you're going to touch something, if you're going to pick something up, well, the only objects you can pick up, like if you're in this plane over here, you know, there's a couple ammo pickups. You can actually just check all of them. You know, am I touching this guy? No. Am I touching this guy? No. Okay, done. You know what I mean? Like, you know, that's an order n collision. It's just terrible. Except there's only two things there. You guys understand? Like, for every one of these, you know, leaf nodes, how many objects are on them? Like a couple, you know, like 4. You know, am I touching this box? No. Great. How about this one? No. Right. Like you can do that every frame, and if there's only like 4 objects in the leaf, who cares? It doesn't matter. It's a box. Testing to see if a box touches a box is like really easy. Even on like a 386 CPU, you could do that at 60 frames a second. It's not a problem. Yep. That's not where the cost of all this was. How about the lighting? Do you guys see how there's like lights and shadows on the map? Voxels are fun to work with. The Quake creator wrote his own code. He wrote his own programming language for Quake. But yeah, all the tools for like the map editors and all that stuff was done by Carmack and Romero and Tom Hall. And he wrote Quake C. He wrote his own programming language to do the game coding for Quake. He wrote his own language, his own preprocessor, his own compiler, and linked it in with the C code. So the C code would call into this interpreted code. And so people who aren't good at engine programming could write the game code, and modders could write game code without being able to hack the server or cause security issues. It would just call into the interpreted code over there. Yeah. Yeah, John Carmack is a god among men. Like, honestly, like, I wouldn't even consider making my own language. You know what I mean? Like, if I wanted to have scripting support, I would just be like, all right, where's Lua? Where's Lua at? You know, let me go get a Lua plugin, you know, and just use that. You know what I mean? Or C#, sure, whatever. You know what I mean? But he's like, he's just gonna flex and just like make a programming language. Like, I honestly, like, I probably have more respect for John Carmack than any other programmer. Maybe Linus Torvalds. It's a tough one. Richard Stallman doesn't really code anymore. Yeah, so either Carmack or Torvalds. They're both just absolute geniuses. Or the guy who made Roller Coaster Tycoon and Assembly. Exactly. All right. So the shadowing, by the way, done here, just as an aside, is done using something called a shadow map or a light map, where basically all of these lights are placed in the world, and then you run a tool on your BSP file, and what it does is it does essentially raycasting. It checks to see, can this part of the world see this light? Yes? Okay, light it. If you can't see it, it doesn't get any light. How much light comes in from the sky? How much light comes in from this light, from that light? The equation to light something is right? You have a surface, you have the sun, light's coming in like this. You dot product the displacement vector and the normal vector together, which is essentially the cosine of the theta. So you have an angle to the sun, cosine of theta. That's what percentage lighting you get. So if you are if the light's coming straight on, it's fully lit. If it's coming at an angle, you get no light. The cosine here, yeah, you can actually see this here. So when my palm is facing, when the normal vector, which is this, is facing the light, it's fully lit, and then as it tilts away, it gets less and less light. It's just a cosine relationship. That's it. And so what they have to do for these light maps, because it's too hard to do in real time. It's too slow to do in real time back then. So what they would do is they would, for every point on the world, they would, and it's a quality setting. You do a draft lighting or you do high quality lighting, which would run overnight. Like I did maps occasionally, and it would take hours and hours to do all the lighting, because it's essentially drawing rays from like all the lights to every point on the world and writing down how much light and how much shadow it gets, and it saves it. And then it just applies that to the surface of the map. So the light map will say this part of the map is shadowed, this part of the map is light. If you have higher quality light maps, you get more details. If you have poor quality light maps, you get these like zigzag patterns. Which will look like a, yeah, I don't know if you can see that. There. You see how there's like this stair-step pattern on that? That's because the light map has samples on every point of the surface. And so if you have a low quality light map, the samples are far enough away, you can see that's shadow, that's light, and it just draws like a stair-step pattern on them. You've probably all seen that in video games before. That's because the pre-computated lighting is just not good. Over here, you can see that. Or the stair-step pattern there. Okay, so the last thing I want to talk about today is z-buffering. So the painter's algorithm is busted. Nobody uses it anymore. I mean, you kind of have to know about it because there's like historical reasons for knowing all this kind of stuff. Nowadays, though, if you're going to draw one triangle in front of another triangle, what you do is you write to something called the z-buffer. So the z-buffer for every pixel on your screen, let's say that your screen has 12 pixels. For every pixel on your screen, when you draw a triangle, like let's say we're drawing a triangle like this, and it's 10 units away, you're going to write into the z-buffer, this is 10 away, this is 10 away, this is 10 away, this is 10 away, this is 10 away. And then if you try to draw another triangle on top of it, if that triangle is closer, if it's only 5 units away, like let's say we're drawing this triangle here, and this triangle is only 5 units away, then that triangle, let's do it in a different color, galaxy colors, that triangle is going to draw on top of the other one. And then you write down into the z-buffer, that's 5 away, 5 away, 5 away. These are still going to be 10 away because they're still going to be visible, but all of these are 5 away. Then if you draw somebody that's further away, you come in and try drawing a triangle that is like 30 away. Like that. All the people in front of it are going to be drawn still. So you're not going to draw any pixels except in this spot right here. We're going to get one pixel. So 1 pixel is visible. The 5 away guy, there's a 10 away guy, and then the 30 away guy only gets 1 pixel drawn. And the reason why this was considered expensive was because back in the day, a kilobyte of RAM was $1,000. And so having enough RAM to actually hold how far away every pixel was considered an extravagant luxury. The person, in fact, who proposed the z-buffer concept said, this is wildly impractical and will never happen. And it became the standard because the price of RAM drastically. $1,000 for 1K of RAM, yes. You don't understand how cheap RAM is these days. We figured out, and by we, I don't mean myself at all, but we figured out how to make RAM really dense and really cheap, and it has made all the difference in the world. You don't, like, computer science people don't check anymore to see if their memory allocations fail. We used to have to do that all the time. Every time you create a string, did it fail? you know, because we might have run out of room with hello world, you know. Like when you have 4 megs of RAM, like that's a real concern, you know. Another example of Kearney outsourcing. Yeah. 64 gigs of RAM, yeah. Is not pricey anymore. So a Z buffer is basically, yeah, for every pixel on the screen, you record how far away that pixel is. Then when you go to draw another pixel on top of it, like these pixels are all red, you know, and that's all actually held in like a separate buffer, like the actual colors you're drawing. You've got red here, and then these are going to be, I don't know, rainbow colored of some sort, and then this one is galaxy colored. Your actual draw buffer is different from the Z buffer. If I'm going to draw a triangle that's going to cover, I don't know, this part of the screen here, and it's only one away, it's going to be right up in my face. It's going to cover up all the other ones. Then what's going to happen is all of these guys lose to the person who's closer. That guy, say it's white. And the draw buffer gets filled with white pixels. The Z buffer holds that they're one away. And so every time you overdraw the same spot in RAM, the Z buffer chooses which one gets shown, which one loses. And the one that gets shown is the one that's closer to the camera. The one that's further away gets occluded by the one. Pretty simple concept. You guys should be able to implement it like with reasonably simple, like it's just a 2D array of floats or whatever. So, that'll be your homework assignment. I'll give you guys a week to do that. Got 50A starting now. So yeah, it's gonna be 3D animation. So it looks like this. So you can see you got your triangles, got a little barycentric coordinates going on there. But like when the triangles overlap, you can see one of them is like penetrating through the other one. That's because each of the vertices is at a different depth from the screen. And so some of them are closer, some of them are further. They're rotating, and then the closer one gets drawn, the further one gets hidden. Okay, so we will push that out. Sudo deploy homework to IS50 3D animation, and I'll give you guys a week to do that. All right. So if you guys need help, just let me know, and you guys should be able to do it. It's a 2D array to figure out the Z buffering. Like start with that. Like draw a triangle, see if you can fill a triangle, and just at every point, like don't worry about the animation to begin with. Just draw 2 triangles and see if you can draw it so that the nearer triangle shows and the further one doesn't. Okay. You've got it's a 2D array. It's just a 2D array of distances. So it's an if statement. So yeah, if you can do Babylon, then you can definitely do this. I have confidence. Didn't even fill triangles yet? Oh, now's a good time to learn.